Hello guys, Cyprien from FA for All here, and let's go for the first Openfoam tutorial, the lid-driven cavity. So this is the first and most basic Openfoam case that you can find, and this is also the one that is detailed in the Openfoam user documentation. So you already have the text if you want to go to the website and have a deep look at all this. But the purpose of this tutorial will be to go with you on how do I actually take this text and interpret it, and how do I run this simulation and understand the result that I'm getting. So some of those aspects, if you're not familiar with CFD and you have never used Openfoam, might be a bit difficult to understand the first time. So that's why I'll try to comment as much as possible when I go through this tutorial. So if you like this video, if this is useful for you, please like it and subscribe to my channel. And if you have some questions anytime along the way, please post it in the comments of the video or on the blog. I look at every question and I try to answer them as much as I can. So let's go. I haven't done so many tutorials about CFD, and this one will be great. And I'll try to make it as short as I can, but there is obviously a lot of content to talk about. And I'll be talking about the lid-driven cavity flow, which is on the Openfoam user manual, so you can have the details on the website. And I'll show you how to do the pre-processing, how to view the mesh, how to run the solve of Openfoam, what are the different files and folders to do that, how to do the post-processing into PowerView, how to apply different kind of filter to view the streamlines, to view the contours, to do some macros, to actually, you don't have to do that all the time over and over again. And I'll go over the remeshing, the mesh grading, the turbulence and high Reynolds flows, and how that works in Openfoam, how you can change your case geometry, plenty of stuff. So if you're interested and you're really starting from the beginning, you can start just from now and watch the entire video. Or if there is a portion that you think is more interesting to you, I'll add some chaptering in the video so you can go into the comment and go to the part that interests you most and watch this part, because I'm aware this video will be long. But this will be definitely very interesting. Let's have a look now at this example. And here it is. So this is a very simple cavity. So you can imagine that there are three walls like this. And at the middle, you have some fluid. And at the top of the cavity, there is no wall. There is a free surface of fluid. And we will apply a boundary condition to this, which is a velocity of 1 meter per second. So the fluid here will move at 1 meter per second, and we expect that the fluid below the surface will be will start to move because of this boundary condition, right? Because here you have walls, and so you want to see some kind of movement, swirling movement inside this cavity. Now, what are the hypotheses of this case? Well, hypotheses, and especially in CFD, are very, very important because they determine what kind of solver you use and what will be the equation actually solved by the solver, what will be the model of the fluid, etc. A lot of those things depend on the hypothesis you do. And here the hypotheses are that the fluid is isothermal. Well, this case, I mean, is isothermal. So the temperature will remain the same. The temperature will not change. The fluid will be incompressible. So this will be an incompressible flow in 2 dimensions. This is extremely important too. And basically this means that because it's incompressible, the density of the fluid doesn't change. And if you look at the equations of Navier-Stokes for fluids,
you'll see that if the density is considered as a constant, you'll be able to simplify those equations and take the density out of it and calculate in a much easier way those equations. So that's why this is important. And if you think about incompressible flow, so what does it mean exactly? It means that the fluid here is a liquid because, as we know, the main difference between liquid and gases is that gas are compressible. They can change volume when you apply some pressure around them, but fluid do not change the volume. So the fluid here will be some kind of liquid state fluid. So probably water, but it depends of the kind of uh, material properties that we give to it. So this will be a liquid. Now, the walls here are fixed, so there will be no velocity around those boundaries. And there will be one velocity of 1 meter per second on this boundary here. Now, another hypothesis extremely important is the laminar speed. So laminar means that the flow here will be slow enough. The Reynolds number is basically what determines if the fluid will, let's say, conserve a certain ordinated state and flow in a, let's say, nice way, or if the Reynolds number become too high, then the fluid will become turbulent, and you'll start to see some vortex form into the fluid. So laminar flow is generally also means that the flow is totally calculated by the equations, and there is no need to add an additional CFD turbulent model to it to be able to calculate the turbulence. So this is, let's say, the most simple case, the laminar flow. And the Reynolds number calculation is based on several parameters, which is the dimension of this cavity is important. The velocity here is important, and also the viscosity of the fluid. So the viscosity of the fluid, the velocity and dimension, those three will determine the Reynolds number. And if the velocity becomes too high, then we will not be able to consider it as laminar. So we'll have to change a solver to calculate it. If the dimensions are too big of these cavities, the same thing might happen. But in this case, everything is decided so that it stays laminar. So that's one of the hypotheses. We will use an uniform mesh, and the Openfoam solver will be used. And here it's written that this is for laminar, hydrothermal, incompressible flow. So if one of those three hypotheses does not hold, then you will have to use another solver. And okay, so I think this is what this case will be about. So now it's time to actually see how to build that with Openfoam and start the simulation. So if I go down and go to the pre-processing, that's when I will show you how to create this model. And because this is the first tutorial and we want to start easily, we're basically using an example case that is already prepared for you. And this will help you to see a bit how the structure of the file is built up and how you can tweak it to run your own simulation afterwards. So you have to understand first how Openfoam is working and how those various files are computed so that you're able to run that. So Openfoam, basically, if you run it like I am right now, it doesn't have a GUI interface. So you'll have to basically work with a bunch of text files into different folders, and change the information into those text files to generate the model. So there will be no GUI for this, only some text files. And this is how you build the text, the structure of this cavity example from an existing model. So to start building up this, I am gonna just follow what is written here and at the same time explain to you what this means. So first, if you have installed Openfoam, like I mentioned in my previous installation video, you should have this Openfoam run variable into your bash RC. So basically, if I do an echo and I just paste this, you'll see that the content of this variable is actually this path on my computer. So when you say cd $ and foam run, it means basically please go into this folder. So that's where my Openfoam tutorial will be copied. So if I open it right now, so I'm just go to this home and here Openfoam, and you see I have a run. I have just one folder here, which is the previous test run simulation that I ran just to show you that it worked. And now I have nothing in this folder, right? So now let's do what I'm told to do. So let's cd into this folder. So you see that the prompt here changes to tell you that now you are located into this folder. So if I do an ls to see that there is nothing into this folder, only this pits daily folder. And now I'll use the command copy r and this. So what does that mean? It means that this foam tutorial is another variable. So let's have a look at where this points to, because it's important to know where those tutorials are actually located on my computer. And you see that they are into the OPT Openfoam 8 tutorial. So that's where Openfoam is installed, basically. And if I go into that computer, so OPT Openfoam 8 tutorials, and you see that I have a lot of stuff into it. And what we are gonna have a look today is incompressible icofoam cavity. So incompressible icofoam cavity. So this will be the case study that I'm gonna copy. But you see, you have much more. You have an elbow also for the icofoam solver, and here you have all the different solvers which are available in Openfoam. So you see that you have a lot of stuff to do. So this is icofoam is real, just a start. But let's start with that. Let's copy and do exactly. Don't forget the point at the end. That's pretty important. And paste that. Enter. And now if I do an ls again, you see that I have this cavity folder that was copied into my my directory. So let's just go back. Oh, okay, let's go back into my home. Yeah, it's here, cavity. So it works. And now let's cd into this cavity. Okay, and now I'm ready to basically play with this example case that I copied. And the first step is to do the mesh generation. So like I told you before, Openfoam uses different text files to basically create your model. So let's have a look at the file structure. So let's open this cavity, and you see that I have 3 folders into it. I have a folder called 0, I have a folder called constant, and a folder called system. So if I open the system folder, I have one file called blockmesh dict, control dict, FV schemes, and FV solution. So the one that controlled the mesh and the model is this one, the block mesh. So I'll just open that. And you can use any text editor. So here I'll use the basic text editor in Linux, Ubuntu. So it's Gedit, I think. And those are basically comments here, so not important. Convert to meters, so that's basically telling you that there is a conversion between the units. Those are the vertices of my model, so basically the points, and you see that they are 8 points. So if I go back to this, you see that my cube here has 8 points, so 0, 1, 2, 3, 4, 5, 6, 7. So what, and so 8 in total. What is a bit surprising is that I told you this is a 2D simulation, right? But you see this is actually a 3D cube. So why is that? And this is because Openfoam, even if you want to do a 2D simulation, you always have to build a 3D model. But you'll have to basically, one of the dimension, and generally this is the Z dimension, will be considered as empty. So there will be nothing in this direction. And the boundary condition specified on this dimension will be called also empty. And this will basically tell the solver that this is not a 3D simulation. This is just a 2D simulation. So we'll just put one layer of mesh in this direction, and we'll mesh uniformly in the two other directions with 2020 cells. So if I go back and look at what is happening here, as we are giving it the 8 points, and the dimension we give here are 1 for X and Y direction. And for the Z direction, you see that it's 0.1. So it's very small regarding the other direction, but it's not very important actually because there will be only one element. And the command used to actually control the mesh, well, is this call into blocks. And we use hex here to use hex mesh. Here, those are the numbers of all those vertices. And this is the number of elements that will be used for each direction of the grid. This is a simple grading that will be grading 0, 1, 1, 1. So we'll see afterwards what this means. And one thing that I can already tell you is that this 20 here means that you'll have 20 elements in X direction and 20 elements in Y direction. And if you just change that to 40 and 40, you will be able to refine the mesh immediately. So just a simple change in the text file here will allow you to control the mesh. And now you have the boundary conditions. So the name you give to those boundary conditions is important. And it has to be the same because you'll have another text file in which the boundary conditions are defined. So I'll have a look at it after, but we can have it. It's not this one. So it's probably in the constant. No. Yeah. So when you will define the fields that the boundary fields to be solved, you see that you'll give a name to the boundary condition, and you'll have to maintain the same name for here and for the one I mentioned in the system control dict. Block mesh dict, sorry. Okay, so this is the moving wall. So this is the condition at the top of the box. So it is a wall, it is applied to faces, and here what you give here are the points which are making this face. If you see here, the points are 3, 2, 6, and 7. So here I give it the same 3, well, in the other direction, 3, 7, 6, 2. And make sure that you give it in a way that it creates a surface. Don't give it like 3, 7, 2, 6. It wouldn't work. So you have to give it either 3, 7, 6, 2 or 3, 2, 6, 7. And those are the 3 fixed walls. So you see this one, and this one. And the last one, the front and back type empty, are the 2 boundary conditions which are necessary on those 2 sides to basically tell the solver this is a 2D simulation. Okay, and you have a last comment called merge patch pairs. And that's it. So with this file that I have here, so it's exactly the same written here, I just have to run one command called block mesh. So now that I am in this cavity folder, I just write block mesh, enter, and it's very fast. You see here that some mesh have been generated. So I have 882 nodes, 400 cells, and this is the number of faces and internal faces. And if I go back to my folder and go into here in the cavity in the constant folder, you see that I have a new folder called polymesh that appears. And this polymesh folder is what contains your mesh. So you can generate this using this command block mesh and the block mesh dict. So if you want, you can open that to have a look, and you see this is basically coordinate of all the elements are into that. So that's it. So if this works without an error, then you'll get your mesh. And to remesh, basically, you just have to change the text file and rerun the command. Now let's have a look at the boundary conditions. So now that we have discussed about the mesh, let's talk about the boundary condition. So if I go into my simulation, my case folder, you see that I have a third folder called 0, and in which I have 2 files. So I have one P for pressure and U for the velocity. So those are the fields that will be calculated during my simulation. And this folder is called 0 because this is the initialization folder in which I will file the data to initialize those fields. So there are no results in this file, and you will see that when I compute, I use a solver and I calculate, I will see appear new folders at different, so 0, 5, 1, 1.5, 2, etc., in which I'll have the results from the simulation into them. And those 2 fields here are important because this is where I will find definition of the boundary condition about this. So if I have a look at the pressure first, for example, so you see that first of all, I have this dimension and I have an array of 0 to minus 200. So what is that? This is actually the dimension, the unit of this pressure. And to understand how to read this, you have to go into, so there is here section 426. So let's open that. And I will have an explanation about this. Yeah. So you see that the unit here is basically correspond to the following. So the first one is the mass, second is the length, third is represent the time, and then you have temperature, quantity, current, luminous, and intensity. So in case of my pressure, so if I come back, so if we look at this unit, we have a 2 here, which represent meter unit, and -2 second, so -2. So, and this is not the unit of a pressure. If you think about a pressure, the unit should be in Pascal, and the Pascal unit in SI unit should be kilogram per meter per second per second square, right? So there is a difference here, and that's why it's written. It's a kinematic pressure. So if you look on Google, you'll find Openfoam user guide, and there is this very useful description of the kinematic pressure, which is some kind of simplified definition which is used for problems which are constant density problem. Because we are incompressible, the solver you use is not using static pressure, it's using kinematic pressure. But what is a bit confusing is that the name, it's the same. It's all written P like pressure, but you see that the definition is not the same. So the kinematic pressure is defined as the static pressure divided by the density. That's why you have meter square divided by second square. So distance square divided by time square unit. So be careful about that, and remember that whatever result you get in using this kind of solver, this will not be a static pressure unit. This will be kinematic pressure. Now, if we look at the different other things we can find in this file, so we have uniform 0. So this is basically saying that all my pressure in all my model at all the nodes will be equal to 0 at the initialization step. Why is that? It's because we calculate the pressure in a relative way, and so the value here of the pressure, the value we give as an absolute, is not really that important. So we can set it to 0 here everywhere. And here we have the boundary condition for the pressure. So we have 3 types of boundary condition which correspond to the different boundary condition we defined in the mesh file. And we see that basically the boundary condition for the fixed walls and the moving walls is the same. It's a 0 gradient condition for pressure, which means that it will be 0 pressure at the wall. And for the last one, the front and back, it's empty. So to say that this is a 2D problem. Now, if I look at, I'll keep this one open, and let's look at the velocity definition to see the difference. Okay, so it's actually putting everything in one. Okay, so this is the pressure. This is velocity. So the unit here, velocity, is meter per second. So it's correct. We see that, and the difference here is that the velocity is a vector. So we have 3 components here for the initialization. So it's initialized everywhere at 0. And difference here is that at the moving wall boundary, the velocity will have a fixed value of 1 meter per second in the x direction. So uniform velocity. And for the fixed wall, we have a no slip condition, and here we have front and back empty. So once you have those defined here for pressure and velocity, the initialization of the boundary condition is done. Now we need to have a look at the physical properties. So the physical properties of this fluid are defined into the transport properties file. So if I go back into my cavity case, you see that in the constant folder you have this transport properties, which actually just contain one line, new. This is the unit. So this is the kinematic viscosity and 0.01. So why only one value, and why is it equal to 0.1? Well, this is written here. It's because we are in this case in incompressible flow, and with this solver Openfoam, we only need one property to determine the fluid, which is this kinematic viscosity. All the other properties are constant and they are already decided, so we only need this kinematic viscosity. Now, how do we set that to 0.01? Well, in reality, we would first look at the fluid which we are using. So we use water, for example, and we'll just input the kinematic viscosity of water. But in this case here, I don't know if the fluid is water. It's probably just some kind of ideal fluid, which might be water, might be something else. And we are defining this viscosity based on the definition of the Reynolds number, because we want to stay in a laminar state. So we want to be sure that the Reynolds number is equal to a value low enough so that we are in laminar state, and the value we'll take here for the Reynolds number is 10. And in order to have 10, we have to calculate this Reynolds number, and you see that dimension, the characteristic dimension is 0.1 meter of my cavity. The characteristic velocity is 1 meter per second. So to get 10 for the Reynolds number, the only thing to set is this kinematic velocity equal to 0.01. That's what is defined here in this file. Now let's talk about the options we have to provide to control the simulation time in the solver. So those information are located into the system folder control dict, where you will find a certain number of fields. So I think start from start time, end time, this is pretty obvious. It means we start at 0 second and we end at 0.5 second. Then there is a delta t, so that the time step will be 0.005. So it means that in total, because the end time is 0.5 and I want a time step of 0.005, I will have 100 increments of time. And then I use 20 for the write interval. It means that I will not write those 100 time interval because it's too much data. I don't want that much data. So I will only write the results every 20 time interval. So that's this means. How do we decide this 0.5 seconds is okay for the end time? And this is a pretty big problem, because for CFD and especially the Openfoam solver is a transient solver. So I have a blog post about difference between transient and steady state. So I invite you to have a look at that on the blog. I'll put a link in the description. But just said simply, when I start at a transient state, the fluid will be not moving at the beginning. It will start to move slowly until it reaches the final steady state, where it will stay at this state. So, and we want to calculate a time long enough so that my simulation will reach this steady state. Basically, it will go from the transient to steady state and remain to this stable steady state. Now we have to know how long how much time is actually required to reach this steady state. So one rule of the thumb, which is generally used, is explained here. It's we use the time needed for the fluid to pass through the domain 10 times to reach the steady state in laminar flow. In this case, the fluid is not really passing through the domain. Instead, we'll take the time it takes from the the time taken for the lid to travel 10 times across the cavity. So which is in total 1 second. So we should take 1 second in total. But what happens is that if you calculate for 1 second, you will realize that it's useless to calculate 1 second, and you just need 0.5 seconds. So this is empirical. This afterwards, after calculation, looking at the results, you realize that you just calculate 2 times what was required. So you can divide this time by 2. So here we just tell you in this example that you can calculate 0.5. Now, of course, you should check that by yourself, and we will afterwards. But for the moment, you should believe that this is 0.5 as the end time is okay. Now that second problem is, how do I know the delta t and that this delta t is small enough? Because if your delta t is not small enough, then your simulation will diverge. So you'll not get convergence, and you'll get a lot of errors into your solution, and you will never get the correct answer at the end. So this is extremely important to choose a delta t which is small enough, but not too small as that it will actually take too long to calculate. So you need to have a delta t which is small enough but not too small. And we use the current number to decide that. And if your current number is inferior to 1 everywhere in the model, then that it means you're good. And so you can take this delta t value in order to get a current number inferior to 1 everywhere. So current number is dimensionless number, a bit that like the Reynolds number, which is defined like that. Delta t multiplied by the velocity u divided by delta x. And delta x is the cell size in the direction of the velocity. And because it has to be inferior to 1 everywhere, we have to take the worst case scenario, basically. So where the velocity is the highest, which is right below the lid, where the velocity is equal to 1. And at this position, the delta x is equal to, so 0.1 is the total dimension of the lid, and we divide it by 20 because we have 20 elements. So that's how you get 0.005 meter for the discretization. And if you take back that into this, in the current number, you get 0.05 second. So that's how you find out that this is a good time step to use. Now here, this is very simple example, so we can do this calculation. In very complex examples, might be a bit more empirical, so you have to basically think about what should be the most accurate time and do some tests and make sure that you're not choosing wrong. You have to choose a good value. Now, if we have a look at the FV scheme and FV solution, you see that you have a bunch of options to control the way the solver actually works. So the interpolation scheme, Laplacian schemes. So all of that is a bit too much for now, so we don't need to discuss about this. And you can just use the default options. Now in the FV solution, because Openfoam is a finite volume solution solver, not finite element, a finite volume, you have a few options for the resolution of the different fields, the preconditioner used, the type of solver used to solve the velocity. So we use a smooth solver. There is a certain tolerance. So if the tolerance is small, then this will take a bit more time to calculate. So here it's, but we want to be sure that we get the correct solution, right? So generally this has to be that small. Then in the piezo dictionary, you get P ref cell, P ref value. So this is referring to the absolute value of the pressure. So we solve the pressure in a relative way, and the absolute value is not that important. So here it's set up to 0, but if you wanted to set that to atmospheric absolute pressure, you could change the value here. But the only thing that would do is that it will, instead of taking 0 as the reference, it will take the atmospheric value as the reference, but that's all. So that's the only thing you need to know for now. So we'll come back to that later. Before actually launching the solver and actually solving the solution, let's talk about the mesh. So the mesh is already generated, like I told you before, but it's useful to have a visualization of it, because here we only understand how it should be, but it's good to see it, right? So for that, we'll use Parafoam. So Parafoam is basically ParaView, but with a special module on top that is able to read the special format for used by Openfoam. So I'm just going back into my terminal, and the only thing I have to do is to launch Parafoam. So from within my case study folder, and the small ampersand sign that I put afterwards, it's not required. It's used just to signify that I'm opening Parafoam in the background. So I'll be able to continue to use my terminal even if I run it like that. And you see that ParaView opens and opens directly my results. Click on apply and you see that. And to see the mesh, you have to go down here and activate surface with edge. And now we see 20 element per 20 elements. So that's what my mesh will look like. So for the moment, there's so if we look at the result here, we have basically only the initial step result. So we don't have the other step. We have only one type of result, which is the first, because it's not calculated yet. So I'll close that and let's come back to the calculation. So launching the Openfoam solver application is just one command. So it's very easy. Let's just run Openfoam like that. And now it's over. It's actually very fast, so you don't even see it, but it calculates each of those time increments have been calculated right now. And if I go back into my folder structure, you see that now I have 0 to 0.5, and I have 1, 2, 3, 4, 5, 6 different folders in which this time I have, so I still have pressure, velocity, and density, and in between but if I open that, you see that I have more results stored into those files, and those are the actual calculated result fields. So of course we'll have to look at those results using again Parafoam, and so that's where you need to have a bit of knowledge about ParaView. So let's open again Parafoam. Apply. And if I go to, let's have a look at velocity. If I apply that, you see that finally I arrive at, and this is my steady state shape of the fluid. So I prefer to have a better view of the colors. So let's open the color map editor. And instead of 255, I'll just use 12 colors. Press enter. So you see that now, you see the fluid like that. And there are a lot of ways to post-process those data. So I'll have a look with you at how to display the different the streamlines and all the things we want to see about those data. And actually, I have a full course just about ParaView on YouTube. So if I actually recommend you to have a look at this full ParaView course, because this is knowing how to use ParaView is extremely important if you want to use Openfoam, and also for many other applications. ParaView is really very useful post-processing software that you will have to know how it works. So the first time it's very overwhelming software because there's a lot of things to understand about this. But if you go through my video series about ParaView, you'll understand very quickly how it works, and it's not that complicated once you understand that. Okay, so let's go and let's continue our post-processing tasks. And it's a good idea to record whatever you do, because this will allow you to make a macro at the end, and you will not have to redo all the same operation every time. So, and the way to do that is just to go in Tools and to start the trace. So after you do this, click on OK. Every operation you will run into ParaView will be automatically recorded. So very useful function. So the first thing to start on this model is to realize. So let me just rotate this. So to realize that this is a 3D model, right? It's not 2D. So we calculated that as a 2D model, but it's really 3D data. So what we want to do is to get to the slice after that in the XY plane. That way we'll be able to post-process like it was a 2D plane, and to get the streamline, to get the various kinds of post-process that we want to see in CFD. So the first way to do this is to go into Filter, and let's go into Alphabetical, where you have all the filters in ParaView. And there's a filter called Slice that will allow you to split your model along one plane. So here you have several ways to slice your model. So here the slicing is along a plane, and the plane here is in red, so you don't see it because it's in the direction of the screen. But you can change this by clicking on the normals here. So if I click on Z normal, you see the red square goes into this plane, and I click on apply, and now I actually created a second view, which is a filtered view along the slice. And because I'm not interested to see this, again, I can hide this cutting plane. So if now I'm rotating the model, you see that now I have a 2D model. So that's what I wanted. So I'm ready to go for the next kind of post-processing. So let's have a look at the pressure, for example. And because this is CFD, I'd like maybe to change the colors. So I show you very briefly how to work on the data on the color map editor. It's good to know also that you can go here on this very small icon with a heart on it and choose certain types of presets for the color. So for CFD, well, generally, I think it's good to have some color with some green in the middle, maybe jet. But that's not that important, but I think it would look good like this. Okay, and this is the pressure with this new color set, so I'll hide that. And now what I'll do is that I will extract contours of pressure out of this. So we see that the pressure goes to minus 4.4 up to 4.8. So I guess this is the kinematic pressure. Remember, I talked about it. It's not so it's not Pascal unit. It's kinematic pressure. And the way to extract this is to use another filter called the contour filter. So I could go again into the filters and search where is this contour filter. Another way to get the filters is to press Control plus space on your keyboard. You'll see this appearing. and then you type contour, you search for the right filter, and you apply the filter by pressing enter. So that's much faster. So you have to remember Control plus space to do this. It's the same than going into the tools, but it's much faster. Now let's go into the property window of this filter and see how to control this. So I have to choose the certain number of values I want for this filter. So there is a small icon here called add a range of values. So if I click here, I'm able to split this range of pressures into a certain number of steps. So I choose 10 step, click OK. I'll still click on apply, that's why you don't see it here. And this will be pressure contour. So now I can click and apply and I can start to see the contours. And those contours are white because there is no coloring here set up. So if I want a coloring, let's say according to the velocity, so those are pressure contour but colored along to the scalar velocity magnitude. And that's what you get basically. So that's the contour. Let's have a look now at another type of result, which is the vector plot. So in order to get the vector plot, I have to either inactivate or delete the contour filter and go back to this slice contour by clicking the small eye icon. So I can activate another icon, because what's important to understand is that each filter is applied upon each other. So if I go to the contour and I apply my glyph filter to get the vector on the contour, I won't see anything because I will be applying the filter to the wrong layer. So I have to inactivate this, click on slice to activate again this sliced pressure layer. This time I'll be looking at the velocity, and I will again control space to get the glyph. So the glyph is the vector type of plot. So I click on that. And here in this side, I can choose the type of glyph I want. So I choose arrows. So let's just click apply just to see what I get. So now I get, first I have two layers are now activated. So I see one on top of each other, and the vectors are not oriented in the right direction. So that's because in the property windows of this glyph, I have to change the orientation to tell it, okay, I want to orient that, with the vector of, and I'm seeing that I'm looking at it in the wrong direction. Should be looking at it like that. I will hide this slice and keep only this vector here, and maybe decrease a bit the scale factor because those vectors look a bit too large. Just apply. Okay, and now I get the vector of velocity. Now, what is a bit weird is that velocity at the wall is 0, so I shouldn't have like a vector going to the x direction on the walls. So from my understanding and what I searched in the documentation, it seems to be a problem of ParaView. So it's just a visualization problem. When the scale array is turned off like this, ParaView will automatically set the value at the wall, which is 0, and it will set the vector in the x direction here. So, well, I could set the scale array to the actual velocity of the fluid. Oh, sorry, not this one. Scalar velocity. And in this case, now well, it's scaled very small, so I'll increase slightly so you can see something. Yeah, so now we don't see the velocity at the wall anymore, but you see really the huge difference between the velocity at the top of the lid, of course, because now it's scaled according to the actual value of the vector. and the velocity here within the box, which is very small. So basically only this velocity here is very huge. So if you don't want to scale, no scale array, and you see every vector here, but you get this this vector at the wall, which is actually shouldn't be here. Okay, now let's look at the streamlines. So another very interesting type of plot. So I'll just inactivate this glyph, go back at the slice, and this time I'll do a control, and so there is a filter called stream tracer. That's the one I want to use. And the stream tracer requires some kind of seed that will determine how the lines are drawn into the model. So for this case, I'll move that to the middle like this. So you could do it graphically, or you could just go according to set the value. So I'll do it approximatively here. If I click on apply, let's see what I get. Okay, and that doesn't look like streamlines, but there's a reason for that. It's because the resolution I'm taking is much too high. So let's say I want only 21 streamlines, and now it starts to look like streamlines for the flow. But I'd like to give it a certain diameter to those streamlines, and for that you have to apply another filter on the top of this stream tracer. So I'll do again a control space, and this filter called tube. And this filter will, so I have to give it number of sides, choose 6, radius factor. Let's try with that just to see what I get. Apply, and now, yeah, okay, so now I'm getting some tubes here. Maybe if it's a bit too large, you can reduce a bit this radius here. So for example, here, let's say it's approximately 1, so I can put that to 0.5, enter, apply. Now it's a bit smaller, so it looks much better. Okay. So that's more or less what the different useful types of visualization. I'll show you a bit more after how to look at the draw some curves on top of that. So we'll have a look at that after. Now let's have a look at the macro that I was talking at the beginning. So I save the trace, and if I go into my tool, now you have stop trace, so I'll just stop that. And you'll get some Python code which represents the way PowerView is basically post-processing every action I did, but using code, using Python code. And the easiest way is to save that as a macro. So there is a macro folder in which you can put some macro, and let's call that cavity post 1, for example. Okay, close that. And if you go into a macro, you'll see that now you have this cavity post 1. So let's say that I close everything. I close PowerView, and now I decide to reopen my results, apply, and you see everything came back to the initial view. I don't have my filter. So instead of going back to all the menus and doing everything I'd done previously, just go to macro, cavity post, you wait a bit, and you should be getting, okay, exactly the same thing that I was looking at. So make sure you go to the right time step. Right now I'm looking at the last time step, the steady state solution. If you are at the first time step, you'll see only one line like this. So make sure you go to the last time step. But you see, in one operation, I am able to view the streamline, the glyph, the contours. So very useful to save a macro like this. Okay, so that was it for this part. And now we'll be looking at how to increase the mesh resolution and how to refine the mesh to calculate small, better solution and more accurate results for this case. So let's go and create a new case for this refined mesh case. So I do like an example. I'll go back and open the folder in which I have my cavity simulation study here. I'll make another directory called cavity fine. So you see now I have cavity fine directory. There's nothing into it. I'll copy using the cp command, and the R comes for copy the directory. So copy the directory from cavity constant. So everything inside this directory will be copied into cavity fine. And let's do the same for the system. So if I open my browser and I look at the cavity file, now I have constant and system folder, which contain exactly the same files than my previous. Now there is no field into it. There's no. If I go back to my cavity, you see that I have those fields, and I initially started from 0. And what I'll do in this case is I will not start from 0. I will start from the last calculated case. So I will take the fields that I already calculated, and I will interpolate that to my refined mesh. So this will allow to calculate much faster the steady state solution on the refined mesh by starting from the already calculated results. But before I do that, I have to refine the mesh. So this is pretty easy to do. The only thing I have to do is to go into the system block mesh dict, and in this hex, instead of 2021, I use 4041. Save that, close it, and now you have to run again the block mesh command to remesh. Okay, so oh yeah, I have to cd into the cavity fine folder, of course, cavity fine, and then do a block mesh. Okay, now it works. It refined the mesh. So you see that now I have 1,600 cells. So I had 400 before, so it's refined 4 times. And now what I have to do is to map the coarse mesh results onto the fine mesh. So the first thing to do is to open the cavity fine system control dict, and here set up the start time to 0.5. So I will start from the previous simulation 0.5 increment. And I will use a command called map fields. That is a command provided for Openfoam, which will do exactly what I need. And if you want to know the options for this map field, you can do map fields dash help, and you'll see the various way to actually use this function. So in my case, the boundary condition and the geometry didn't change. So you see that I have to use consistent. And the only thing I need to give it is the case of my source directory. So the way to use this map field is map field, 2 dots to say I'm coming back to my previous case. I give it the name of the case, cavity, and I use the command dash consistent to say that the boundary condition and the geometry didn't change. Enter, and now the interpolation has been done. So it created database as time, source times 0.5, it created the mesh, and the source mesh was 400, and target mesh is 1600. Very nice. It's actually pretty easy to do this kind of thing. I saw other solvers where it wasn't as easy to do this kind of interpolation. Okay, now we'll have to do a bit of control adjustments on. So let's open again my control date. And so it's written here what we need to do is we need to maintain this current number less than 1. So that's what I described previously. And the way to do this here, because we multiplied the mesh, so to get the same density, the mesh size was 20, now it's, the number of elements was 20, now it's 40 per 40. So this makes that, if we do the calculation, the delta t should be half of what it is now, so 0.0025. And now we'll change the write control method. Instead of running a certain number of time steps, we will run for a certain number of time interval. So what it's written here is that I have to replace the write control by, instead of using time step, I have to use runtime. Make sure you get a capital for the T. And here, instead of the number of increments, I have to give it a number of time intervals, so 0.1. And the end time will be 0.7. So previously I needed 0.5 second to calculate everything. Right now I already started from a solution which is almost computed. I just have to refine according to the mesh. So I'll use 0.7. So I need less time to basically recompute those results. And this should be good to go. So Control S to save. And now I just have to run again the solver. So a small trick is to run the solver in the background as a background process. And you can use this to save what the solver is actually doing into a log text file. So that will allow you to come back later to have a look if you get some problems. Because if you run it in the background, you don't see what is basically happening if you don't do that. So Openfoam, and so this will basically redirect the standard output of the solver into a log file. And the ampersand sign tells it that it will run in the background. So I enter. And when I do that, you see this. So this is the background process ID, which means basically that it's running somewhere in the background in your computer, but you still have the control over the terminal. So that's pretty cool, but you don't know what is happening. That's why I saved it into a log. And the way to see the log is, well, if I do ls, you see that I have a log file that is now here in this folder. So I could just go here and cavity find and open this log. And now you see this is the result of the execution. So obviously this is finished, 0.2. It's pretty fast, so yeah, it doesn't take long. So it's finished. So now I can have a look at my refined mesh results. So just use Parafoam, run that in the background, and apply. Let's look at the velocity and last time step. We see the result already looked pretty much refined. Let's change the color map again to 12 colors. I should set that as a default because I really don't like the 256 colors. It's too much. So, okay, and you see it's much smoother than before. And I can use the same macro I recorded previously, so I don't have to go through all those steps again to create the filters. Okay, and now if I want, I can just have a look at, again, this tubes or glyphs, right? So you have much more points, so that's why you have much more results looking on the screen. Now, what if you wanted to, let's say, display both results at the same time, so the unrefined and the refined? So I will let ParaView open for this, and what happens is that when you run the the Parafoam command into here, it creates automatically a result file, which is called cavityfind.openfoam, and that Parafoam reads to be able to have a look at those results. So if you don't have this file, what you have to do is to, let's go back to a previous cavity simulation, LS. Okay, I have it, but if I didn't have it, I'd have to use Parafoam and touch like this, touch, and this will create this file. And so it creates the cavity.openfoam. And when it's created, you can go in ParaView here and you can open that cavity openfoam file. Yeah, and you get it like this. So hide this. Again, let's have a look. This is the unrefined last time step. Let's do again this macro. So that's how you see the macro is useful. Okay. And yeah, so just look at the slice results. So this is my, if I look at the edge, this is the unrefined result. And this is the refined results. So where the mesh is much slower. I could look at like that. One, so refined case and unrefined case, slice like this. And now you can see the difference, right? This is much smoother, so you have much more density of results in this case than in this one. So you can compare both results. Okay, now let's talk about some of the additional post-processing options that Openfoam offers. So let's head up again into our CavityFind project. And let's have a look at the post-process function. Post-process. And to see what it does, there is an option called list, which will give you a bunch of functions that are available. So it doesn't describe in detail all what those functions do, so you'll have to go into documentation to know about this. But what we are going to try is this function, func component u. So what this does is that it takes the vector u, which is calculated on each time increments, and then it prints out the scalar components ux, uy, uz, and it just saves them into each of those time steps. This will allow us to draw some graphs and curves of the components. So let's use this function. So I'm in the CavityFind project, func components of u. Okay, enter. Now you see it goes through each of the time steps and it basically prints out the components. So how do we view that and how do we use this to draw some graphs? Well, of course, we have to open Parafoam again. So apply, and we had already some data into it. So in order to update the data with the new information that have been added in each of the time steps, you have to go in the property window, refresh times button. So click on that. If you go down, you see that in this fields, you will have new UX, UI, UZ that will appear. So Those have been generated by this post-process func components U function that I just used. So what I'll do is that I will select this and select the other ones. And also make sure that in the mesh parts here, you only select internal mesh. You don't select moving wall and fixed walls. So we don't want the data on the wall, only the data on the internal mesh. Otherwise, my curves might be a bit off. So make sure you do that. Click and apply. Okay, so you see the components here are now available here to view separately. So we could already view them through the vector. Well, if I activate vector again, view the vector and see them here. That's the same thing. Yeah, it's exactly the same. So actually, you don't really need to do this. So it's just to show you some of the post-processing options available. Okay, so now that we have this, so I unactivate this again. What do we do with that to plot that as a curve? Well, again, we use a filter. So filters, and I think it's in data analysis, plot data over time. No, plot over line maybe. Plot over line. Let's try this. So I have plot over line, and I have basically to apply that, and we see that it basically show you some data here. So if you click on the charts and you go down, you see what is currently drawn on here. So I'm only interested to see UX, for example, so you can inactivate some of those. And this is the UX curve. So we have this curve traced right now, but what we have to figure out is from where those data are actually taken. So where is this? Where are the points taken from this? So I should be able to view this line. Oh, okay, I know why. It was shown, but it's actually shown inside the model here. That's why. So you know what I do? I just close that. I will delete this, and I'll do a slicing filter first. Okay, that way it's a 2D, because if it's not 2D, that's why I'm having problems to see the curve. Okay, and now that that plot over line, that's what I did. Yeah, plot over line, and now you see the line, right? And what you can do also is you can put the mouse in one place and you press the one button on your keyboard, and this will reposition this at the right position. Click apply, and yeah, now the curve looks much better than what I expected. So this is how it looks. The velocity UX plotted from the y equals 0 to y equal 0.1 meter. And it looks like this. So I'm able to draw this curve. Now, if you want to change the way this curve is drawn, you can click here, and you have some options like put some dash, changing the color, etc. Put some legend over it. Well, I won't go over this kind of options. I think you understood how to draw this kind of curves. And after that, you can save it as a picture. And if you want, you can make a macro as well, like I did previously. So this automatically done. Okay, so now we're good to go to the next. Let's have a look at how to do some mesh grading this time. Let's talk about mesh grading right now. So when I started the first time to do this example, this was one of the parts that was the most difficult to understand, actually, why this mesh gradient works like this. So I hope that I will be able to bring some light to you on why this is defined like this. So the first thing is that we'll have to modify the block mesh file to generate um, a model, a mesh which is much more complex. Well, not that much complex, but it adds some new points, as you see, and it divides the full volume into 4 different x's. And then we'll divide the hex command into 4 and use the simple grading to actually um, to do this kind of graded mesh. So let's have a look at how we can do this. And because this case requires a lot of modification, this is already provided into the example. So I'll just copy this. And what I'll do is that I'll do a copy into my directory CPR of this cavity and a cavity graded. And don't forget the dots to copy here. Okay, let's see if the copy worked. Okay, it worked. I have a cavity grade new case right now. So let's cd into this cavity grade. And let's open the block mesh file. So I'll use Emacs. You can use any text editor. Block mesh dict. Okay, and this is the way the mesh is defined. So what was the most difficult to understand for me at first is why why you have 4 x's and how this simple grading is actually working. Why do you have 2, 2, 1 here, 0 0.5, 2, 1 here, 2, 2.5, 1 here? But to understand that, first let's have a look at what the mesh actually looks like. So for that, let's do a block mesh. Block mesh. Okay. And let's use parafoam to actually view this mesh. Surface with edges. Okay, but this is what it gives. So, and this is, as usual, this is a 3D model. So you see it on one side, but it's a 3D one. And you have this kind of grading that goes smaller when it's against the wall, x equals 0, and x equal 0.1 meter. At the middle here, it becomes larger. So basically, this is this kind of grading that we created. Now, how does this works with those factor that I gave, 2, 2, 1? If we look at this, the hexes, this is the first hex. So the 2, 2, 1 corresponds to the x, y, and z direction. So the 1 is easy to understand because it means that this is the z-axis, which always stay the same. There are always 10 elements in x and y direction, so the number of elements doesn't change. It's only the grading that changes. So this number here is actually a ratio between the size of the last element on the size of the first element here. So if you look at this, you look at the last element here and you look at the first, the last element on this line will be 2 times the size of the first one. But if it's like that, why do you have 0.5 here? So in order to understand this, I made a quick image that will make it very easy to understand. So this is what the mesh looks like, right, in ParaView. And if you look at the grading, the direction of x doesn't change. And if you look at here, when you are on the first hex, the first mesh here over the first one, this is 2 times the size, right? But if you look at this one, the second hex, the size of the last one is half the size of the first one, simply because the direction is inversed. So here it's the simple grading ratio is 2, but if you look at this hex here for the x direction, the grading ratio is 0.5 actually. And when you are on the hex 1 and 2, the y direction is always 2. But if you go to the hex 3 and 4, the y direction becomes 0, 5. And now you understand, I think, why you get this kind of numbers. So, okay, now that this is explained, we need to change a bit some of the parameters for the control to run this. And it's explained here because the grading is a series. You can calculate that the mesh cells using this kind of formula. So I will not read all of this. You can have a look at that. And the conclusion is that the conclusion is that the time step delta t should be reduced to 2.5 milliseconds and the right interval set to 40 so that the results are written out every 0.5 seconds. So in the control dict. So let's do this. Let's open the control dict. And let's have a look. So delta t, it's actually already set up to the right value, 0.0, so 2.5 milliseconds. And the right interval is 40, which is also good. Start time. So start time needs to be set. The final condition of cavity find is 0.7 since cavity and cavity find converge. Well, yeah. So start time. Okay, so the start time here should be 0.7 and the end time should be 0.8. So we'll do like I did previously with the refined mesh. I'll take the actual result of the field obtained at the end of the refined mesh to recalculate this. So let's save and close this. And again, we need to use the mapping fields to map the result from the cavity find onto this. So map fields, cavity find, consistent. So just to remind you what this does is that it takes the already calculated fields from the cavity find case that I calculated before, and because the mesh is consistent, the geometry, the boundary didn't change, this will take the previous fields and apply them. So this does an interpolation at 0.7. Let's have a look at what is in. And you see that now you have a folder called 0.7 that appears. So that means the mapping actually works. Now we can run Openfoam. Openfoam. It's actually very fast because we already calculated most of that. And we can have a look at the results. So parafoam. Let's look at the last time steps. And this is what we get. So I could have a look and compare that with the first and the second cavity find. And this would be interesting to have a look at what is the difference. So, okay, so that's it for this part. Now let's enter into high Reynolds simulation. So now we'll start to see a bit more turbulence coming in, and we'll have to switch to another solver. So here again, I'll use a case which is already created, cavity high RE, high Reynolds, to start doing this. So let's have a look. And you see there is a command called run, which is pretty useful, which allows you, well, it's just to come back to the main folder. It's not that not that interesting, but just in 3 letter you can come back to your main folder. And there is another command called foam clone case that will automatically clone a case at the latest time. So I'll use this one for this. And foam clone case latest time. So instead of taking the initialization time 0, it will copy the last calculated time. Cavity high RE. Okay, so did it work? Create a new case. Unknown option. Oh, okay. I think I did a mistake in the option. Should be latest time. Yeah, right. Okay. Now I have my system. So you see it tells you which directories were copied. So the system, the constant, and the 0.5 directory. Then we can cd into the cavity high RE. Now, how do I increase this Reynolds number? So we want to increase it by 10. So we had Reynolds number equal to 10. So I want a Reynolds number equal to 100. And the way to do that is just to increase the kinematic viscosity. So as per definition of the Reynolds number, this is the only way to control here this. So let's go into constant and transport properties. And you remember my new was equal to 0.01. So now if I want to make the Reynolds number 10 times higher, I have to add a 0 here. And that's it. Now the thing is, well, I also have to change the control data, so I'll do this. But the thing is, right now, I will run that without adding a turbulence model. So, which means that I will still be in laminar. Well, I'm not really more, I'm going further and further from the laminar state. But I will still run it using these settings. So the solver will have more and more difficulties to calculate that, because more you have a Reynolds number which is high, more you'll have a behavior of the fluid which is not very conforming to what we saw previously. You'll start to see whirling in the fluid, etc. So the solver will take more and more time to solve this. So afterwards, in second time, we'll have to use a turbulent model and another solver to solve this. But for this case, we'll just see what it does. It's just to add and see if the speed is really longer to calculate. So so let's now go into system and control dict. And now I have, okay, so the latest time, the most recent time, the end time should be 2 seconds. So I want to calculate that for 2 seconds. And start time should be latest time. So if I do this, it will automatically take the latest time available into this file, which is 0.5, right? So it's going to calculate from 0.5 to in 2 seconds afterwards. Okay, and now to run the code, you have 2 new options that are explained here. No hop, nice, and so what does this mean? No hop, it's a command which enables you to keep running after the user who issued the comment has logged out. So very useful to run that in the background. So you can run this, and if your simulation takes the night to complete, you can log off your account, and this will continue to run. And the nice will change the priority of the job in the kernel scheduler. So it will basically it put a very high priority. So 20 is the highest priority, minus 20 is the highest priority, and 19 is the lowest priority. So this is useful if you want to set a case running on a remote machine and you don't want to monitor it. So it will be put a low priority, and then you can log out, and this will continue to run. So let's try this. So I'll just copy this command, paste that here. Okay, and now this should be running. So if I want to see the log, I could do like that, cat log. Wrong token. Okay, so there's a little problem in my file. Okay. Time. Latest time, I think, from function. Wrong token type, expected scalar. Okay, I think I did a problem when I changed the control date. So start from, okay, I see. So 0.5. So instead of putting start time here, that's here actually, like latest time. I changed the wrong place. Sorry about that. Okay, let's try again. No hub. Okay, now should be running, and I can run the cat log. So now you can see, I'm not sure this is finished already. Execution 0.27. Yeah, it's finished. A good thing to understand also is when do you see this actually converged? Well, you have this FV solution folder. So if I open the system FV solution, and you see that you have a certain tolerance for the solving of the pressure and the solving of the velocity. So velocity is 1 power minus 5, and pressure is 1 power minus 0.6. And if you look in the log here, you see that it tells you that every step it calculates, you have the final residual, which is written here. So if this number here, and also the number of iteration it took. So if this number written here is smaller than the tolerance, this means that basically your pressure converged or your velocity converged. So that's how you see the convergence. And when this is converged, this basically stops, and you get your solution. Okay, now this should be calculated. We can have a quick look. So parafoam, apply. So this is it. And I don't see much difference here, but we see, oh, this is not the last step, right? Yeah, okay. This is the last iteration. So you see that higher Reynolds, the fluid goes like that. So let's use my macro to have a look at the flow lines. Etc. So if I have a look at my yeah, my stream tracer. So you see that the flow is now not the same. It goes towards this direction. And contours are also a bit different. So that's a difference when you are on higher Reynolds. Now, okay, so I told you that we didn't change the turbulence model. Now, I just increased this Reynolds number by 10 times. What if I wanted to increase it by 1,000 times? So the more you have a high Reynolds number, the more you'll start to see some turbulence appearing, vortices in the corners, and basically what you'll have to do is also to mesh much smaller around the borders of your model to actually see accurately what is appearing. Because if your turbulence is very small, you have small vortices forming and your mesh is too coarse to actually represent this accurately, you will not be able to visualize correctly what this does. And actually what that means is that after a certain number, if your high Reynolds becomes really too high, it becomes really impractical to refine the mesh small enough to see accurately the flow. So what we do generally is that instead of solving like that in laminar flow, solving all the equations, we solve an approximated version of the equations to which we add a turbulence model. So what this is that we solve the mean behavior of the flow, plus we give a special model to the fluctuation of the flow around the mean. And there are many models available. And the one in this example is the K epsilon model that with wall functions that will be used to solve this. So it's much too complicated right now to explain you what is this K epsilon model and different kind of models. There are so many turbulence models. This is one of the most difficult things in CFD to understand which is the most accurate turbulence model. So I'll just use what is written in this example and show you how that works. And then if you want, you can dig deeper into the different kind of turbulence model. So we'll use the K epsilon model here, and the Reynolds number will be equal to 10 power 4. So we'll need two extra variables to solve that. The K, which represents turbulent kinetic energy, and epsilon, which is the turbulent dissipation rate. And this time, to use that, we'll need to use a new solver called Openfoam to solve this. So let's copy again a case which is already provided. So this is pretty easy. So I'll use run to come back to the main directory, and then I'll do paste of that. Just copy this. Okay, and now I will cd into my cavity RAS case. Okay, so let's have a quick look at the new files into this. So in this system, the system directory seems to be the same. So, well, there are some changes inside, of course. The constant directory, it's also, oh, you have a new file called momentum transport, which wasn't there before. And the initialization file, okay, oh, you have much more. Now you have a not K epsilon, nu tilde, omega. So those are different kinds of parameters. So if I look at what is written here, so mesh grading towards the wall is not necessary when using the K epsilon model. So that's a good thing. So instead of doing a mesh grading towards the wall, we'll use a range of wall function models. So the wall function which will actually replace the kind of grading towards the wall, so by certain function. And this is in the boundary. So the choice of weld function model as specified through the turbine viscosity field in the 0-knot file. So if I open 0-knot, so you see this. Those are the three boundary conditions: moving wall, fixed wall, and front back, and you have knot K wall function. So this wall function is defined here. And now you have two new variables, K and epsilon, which are saved in K like this. And you see there is a value for that, 0.00375. And if I look at epsilon, the initial value is 0.00754. So how are those values calculated, and what are those K and epsilon? Well, this is written here actually. So it's a bit more complex in terms of theory to explain this. So you should read that very carefully, because this is important and is generally something that new users don't try to understand too much in detail. But this is important. If you choose wrong parameters for the initiation of the turbulence, well, your model is just wrong. So you have two formulas for the K epsilon, which are defined like this. And you can basically calculate those two factors. And here you have the formulas where this is calculated. And that's how you get those values. Now, you have different methods to calculate the turbulence. So you can use RAS, like I'm doing here, or you can use large eddy simulation, LES, in Openfoam. So those are different types of simulation, and LES needs much more calculation power to run that RAS. So generally we use RAS, and so the way to define the to choose the turbulence model is in this momentum transport. So this file that you have here, system, sorry, not system, constant, momentum transport. That's where you define the K epsilon model. And you have plenty of other models. So you have here in this section, you have defined the different types of turbulence models. So as you can see, the three main types are laminar, RAS, and LES. And then incompressible RAS turbulence model, well, you have all of that. So you can really choose a lot of them. But again, a bit too complex to explain that now. So so now I need to update the transport properties. Make sure that this is what will give me a very high Reynolds number. So you see it's very low. So I will have now a Reynolds number of 10 power 4. And I need to set up the control dict as well. System control dict. Let's have a look. This is so start time, end time 0.005, 10 seconds. Okay, I think it's already defined correctly. I don't have to change anything. So to calculate 10 seconds, we see delta t of 0.005. And now I'm ready to run that. So let's just run piezo foam. Okay, I forgot to mesh that. Yeah, block, mesh, piezo foam. Okay, now it's calculating. So just have to wait a bit. So as you see, it's much longer to calculate. So it took 4 seconds. So that's not that long. So it's still pretty fast, but it's a very simple example. If you think about the real life CFD simulation we do, you need several hours, sometimes several days to calculate something. And you can have a look at the residual, which is well, 0. Yeah, so it's monols, and this means this is solved. Now we can have a look at the results. So parafoam, and now you have much more time step, and you can see the result looks totally different at high Reynolds. This is the last step. It's really not like what I had before. And let's use my macro again to see the streamlines. So you see this macro is very useful. Let's hide that. And yeah, the flow line looks like this right now. So this is really, really different. Maybe I can increase a bit the resolution of the stream tracer. Now I have 21. Let's try 100. Okay, so the flow is like this. So it's really very different from what I had before. The last example for this tutorial, which is pretty long, I have to say, is what happens if you want to change the actual case geometry. So create a new case, but which has a different geometry shape. So for example, like this one. So initially I had this this patch area here. Now I want to remove this. What would happen? So I could change this, of course, this geometry. So the number of points here and the mesh. But I'll have to define the fields in a different way because the boundary condition can change as well. And here in this case, instead of calling moving wall this boundary condition, the name has been changed to lid, just to show you that it's possible to change the name of some of the boundary condition in a case that you want to remap. So how will it work? So let's try that. So let's, again, the case is already defined. So let's go back to run folder. Let's copy this cavity clipped, and let's have a look. Let's cd into the cavity clipped folder, and let's have a look at this block mesh dict file. So it's like this, like the example, lid, etc. So that should be okay. Let's mesh that, block mesh. Let's have a look at the mesh before I compute anything. Always good to make sure that I have the correct stuff. And indeed, I see my mesh is like that, and I have an area which is missing. So I have an area missing, and I have a boundary condition which has a different naming. So in order to map the result from my previous case to this case, I'll have to do a few more changes. So to map the cavity results to this, first of all, I must be sure that I have the time directory for this. So if I go back into my cavity, I see that my last time step is 0.5, so that's the one I want to map. And if I go back into my cavity clipped, I have only 0. So I need to make a new folder for this 0.5, cp are, I'll just copy the 0 to 0.5, right? So I need to have this folder and this folder at the same position. And the second thing is that, let's have a look at it here, cavity clipped constant system. So if you look at system, I have a new deck called map fields ticked. So when your mesh is inconsistent, you need to add this file, and you have two functions here, patch map and cutting patches. So this is a way to redefine the boundary condition. So the lid here is the new name, and this will replace the moving wall condition. So this will patch the moving wall into lid. And cutting patches here, well, I do not have that, so I do not need to define this. So now that this is done, I need to use again the map fields command, give it my cavity case, and this time I'm not adding the consistent keyword. I'm just entering this, and the interpolation worked. So now I can run Openfoam and solve that. And it's done. So now let's have a look at the results. Openfoam. Let's look at the last time step, and you see the flow is different again. Let's do the macro to see the streamlines. And now we see that in this space here, you have a small vortex forming. So that's pretty interesting. And that's all for this first tutorial. So I hope that was useful and that was very interesting and that you learned a lot of things. Thank you so much for watching, and I hope you'll give a like to this video because it took really a lot of time to create, and I hope this is useful for you. Thank you so much. See you next.